also want to compare.
All right, thanks. So is there a pointer? Okay. All right. So first, yeah, I'd like to thank the organizers for inviting me. It's always great fun to come back visit Boulder. So I was asked to give lectures on applications of topological integers. So you may be wondering what topological integers are good for, and in fact, I'm wondering about the same question. So as you probably know, there are many proposed technological applications of topological integers. For example, the surface states of topological integers have a very robust spin momentum locking, so that electrons moving in a particular direction has a definite spin polarization. So because of that, if we pass a current, then the current is automatically spin polarized, almost close to 100%. And so there are proposals, many proposals, that this is good for spintronics applications, basically using electron spin for information processing. And 2 years ago, there's an experiment from Cornell group, indeed showing that once we pass a current on the thin film of topological integers, that the spin that is accumulated on the surface is strong enough that it can reverse the magnetization of a neighboring magnet, or causing the magnetization of the magnet to precess. This is something called the spin transfer torque. And according to this paper published in Nature, that this effect of the spin transfer torque is extremely strong in topological integers. So there may be interesting device applications in areas of spintronics. And the other, for example, widely discussed topic is a connection between topological integers and thermoelectric materials. It just seems to be an empirical fact that all topological integers are pretty good thermoelectrics. And so people have been asking questions why. And by now, I think it's pretty much agreed that the surface states of topological integers do not play any direct role in the thermoelectric performance, just because these thermoelectric materials are actually used in everyday life. These are bulk materials. The surface to bulk volume is extremely small, so the surface state does not play any direct role. But instead, maybe the complex band structures that give rise to topological integers may also happen to be good for the thermoelectric performance. Anyway, so there's a lot of interesting ideas for applications of topological integers, and their experiments are catching up. But it's fair to say that up to now there's been no, let's say, killer app of topological integers in terms of in real life. But that is not uncommon. For example, when the metal aluminum was first discovered in the 19th century, it wasn't much used in any interesting way. And the real application of aluminum came about in the 20th century, when people use it as a lightweight material for making airplanes. Okay, so this kind of a delay between the discovery of materials and applications is not uncommon. So instead of talking about proposed technological applications, I'll focus on mostly theoretical applications of topological integers. The fact that these discovery of these topological phases has improved, greatly advanced our understanding of quantum phases of matter. So So this is my rough plan for the 4 lectures. So I'll discuss these 3 topics: the topology, sort of the topological phases protected by crystal symmetry, and then move on to sort of topological phases constructed out of Majorana fermions. So we have heard a lot about talks about Majorana fermions in all sorts of systems, and there's a growing evidence, I think pretty overwhelming evidence by now, the existence of Majorana fermions. So then we can think about now an array of Majorana fermions and use these Majorana fermions instead of real electrons as the building block of phases of matter. So this is what I mean by topology with Majorana. Okay, so and then in the last lecture, I will describe some recent work that I'm very excited about. Sort of, we stumbled upon this direction by thinking first about topological phases with Majoranas, but it led us to new kind of topological order with fractional excitations. But these fractional excitations are not annuals. Okay, they in fact they are immobile. Despite we start with a translational invariant system, that point-like excitations, for fundamental reasons, cannot move as a coherent excitation. So in this case, it's not meaningful to talk about the statistics anymore. So we don't have any anyons. Anyons is referring to the any statistics of point-like excitations. It turned out that these new kinds of topological orders that we have point-like excitations that are immobile. So something we call fractons. It's a fraction of a particle, but we cannot talk about this statistics. Okay, so so with that, let me start with the first lecture. So as you probably have heard a lot in this school so far, that this topological insulators led us to think more deeply about how symmetry and topology interact with each other in quantum phases of matter. And in particular, we know that topological insulators are special in the presence of time reversal symmetry. So they are distinct from a atomic insulator when time reversal symmetry is present. But if time reversal symmetry is externally removed, then topological insulators are adiabatic connected to atomic band insulator. So in that sense, these Z2 type of topological insulators are protected by time reversal symmetry. So so since then, there's been a lot of activities, interests in finding new types of topological phases protected by other symmetries. So this is what Xiaogang is calling symmetry-protected topological phases. So we now understand that topological insulator is a special example of this more general concept of SPT. So the question is, in real materials, what are other symmetries and other SPTs? Okay. Now, if you think about it, that there are not that many symmetries that are present in the real material. For metals and insulators, we have charge conservation symmetry, and for systems with no spin-orbit interaction, we have a spin rotational symmetry. But otherwise, it's hard to think of many sort of internal symmetries. But on the other hand, sort of every solid, every crystal has a lot of spatial symmetries. These are, for example, rotation around some particular axis, reflection, or even translation by a lattice constant. So, so this led to this concept that there are topological insulators, new class of topological insulators that are protected by crystal symmetry instead of time reversal symmetry, and these can be called topological crystalline insulators. Potentially, these could be a very widespread. And for example, we know that in 3 dimensions, there are 32 point groups, 230 space groups, and thousands of magnetic space groups. So the question is, can we take advantage of these crystal symmetries and find these kind of topological crystalline insulators? Yes?
What's a magnetic space?
Oh, it's basically translation combined with time reversal symmetry, for example. So it's spatial symmetry combined with translation. So for example, if I have an antiferromagnet, then translation doesn't restore the system back, but translation followed by time reversal does it. This is a magnetic space group. So So there's a lot of interest in these topological phases, and we now know that they exist both within the band theory that can be described by non-interacting electrons, similar to the topological insulators, but also there exist strongly interacting topological phases that cannot be reduced to non-interacting electrons, and yet these phases are protected by crystal symmetries. So at this point, a complete classification, as you can imagine, that for such a large number of symmetries has not been achieved. There's a lot of interesting work that's being pursued, but we think that at least there's some general strategy in finding these topological phases. So an early example of such phases is a topological crystalline insulator. This is within band theory that are protected by the fourfold rotational symmetry in the tetragonal crystal. You can think of it as stacks of square lattice. So there's a rotation symmetry along the z-axis. And in this particular example, this kind of a topological phase, it does not require a spin-orbit interaction. So within the tenfold classification scheme, this is within the class A1. Okay, and as you can see that the surface of this topological crystalline insulator has quadratic surface bands that touch each other at a high symmetry points, and this band crossing is protected by the fourfold rotation symmetry. Now, yes. Is there a particular reason that quadratic? Oh yeah, the reason is that this is a system with no spin-orbit interaction. So instead, what is playing the role of spin is a px-py orbital, the orbital degrees of freedom. So for spins, it transforms as it's a half integer object, but for orbitals, it's an integer spin system. So with this difference, it leads to the changes dispersion from linear to quadratic. Yeah. Now, this is just a theoretical toy model, but it I think illustrates two things. One is that the surface states of these topological crystalline insulators can be very different from the Dirac dispersion of topological insulators. And second, the point I want to emphasize is that the surface of a crystal has lower symmetry than the bulk. In order to find topological phases with interesting surface states, we have to use the symmetry of the surface. Okay, so it's really the symmetry of the surface that matters as far as gaplet surface states is concerned. Okay. Okay. So now, so as I mentioned, there's a lot of theoretical study of such topological crystalline phases in insulators. Also, there's extension to superconductors. But in terms of the materialization, there are two classes. So a few years ago, with my student Tim Xie, so we found these topological crystalline insulators that are protected by a reflection symmetry. Okay, x2 minus x reflection symmetry in this tin telluride family of materials. So these are semiconductors in the 4-6 family. The tin is a group 4 element, tellurium is group 6. And very quickly, experiments confirmed our prediction by observing the symmetry protected surface states. And earlier this year, there's a beautiful work from the Princeton group led by Andrei Bernovik, and the key player, Iris, is here in the audience. So they discovered a material. This is potassium, mercury, antimony, right? Yeah, okay. Yeah, so in these systems, there's a glide reflection symmetry. This is the first example of a topological insulator protected by a non-semorphic symmetry, or materialization of such a kind. And glide reflection is a combination of translation by half lattice constant followed by reflection symmetry. And also in this material, time reversal symmetry is necessary. So by the combination of the non-semorphic space symmetry and time reversal symmetry, this material is predicted to be topological with interesting surface states. And I think just a couple of months ago, there was a experiment from Hong Ding's group in China confirming this theoretical prediction. So, and as I said, because of the large possibilities of space symmetries, I think there's a lot of possibilities in the future for discovering new types of such phases, and I certainly hope the next material doesn't take another 4 years. So, okay, all right. So let me in this lecture today, I will focus mostly on these topological crystalline insulators with reflection symmetry, and in the next lecture, I'll say a bit about these new class of materials with non-symmetric symmetry. Okay, so tin telluride, this material has a rock salt structure. Consists of cation tin and anion tellurium arranged in an alternating fashion on the cubic lattice. So this is the same structure as sodium chloride, just salt. And so with this very simple cubic structure, there are many crystal symmetries, but it turned out that the important symmetry that led to the topological protection is a reflection symmetry with respect to 110 mirror plane. So there are in total 6 equivalent such mirror planes. And reflection symmetry is actually very special when it acts on the spin 1/2 particle. So the precise definition of reflection is that there's inversion, x, y, z go to minus x minus y minus z, combined with a twofold rotation, for example, along the z-axis, along the mirror axis. So let me call that axis x. So with the combined operation, x go to minus x, that's what you expect. But it has interesting action on the spin, okay, on the spin of electron. On the inversion, electron spin does not reverse direction because spin is a pseudo vector, like magnetic field. It actually is invariant under inversion. And on the twofold rotation, we know that a spin 1/2 particle, when we rotate by full circle, 360 degrees, the wave function pick up minus sign. So that's why reflection symmetry, being a combination of inversion and the twofold rotation, satisfy the property that m squared is minus 1. Okay, if you're doing mirror twice, you get minus 1. And also, because again the spin is a pseudo vector, that if you do reflection x to minus x, the spin of the electron changes in this way. The y and the z components of the spin change sign, but the x component does not. Okay, so this is a very peculiar, peculiar property of the reflection symmetry. And now how does this reflection symmetry play a role in this material? So for this purpose, let's actually compare these two materials in the same family, tin telluride and lead telluride. So tin and tellurium are both group 4 elements. Lead is one row below the tin, so they're on the same column. They have very similar chemical properties. It has been known for decades that tin telluride and lead telluride are both narrow gap semiconductors with band gap that are comparable. And also it's known that the two elements, lead and tin, can mix with each other to form an alloy, lead tin telluride. And as a function of this alloy composition, when X, the tin composition, is around 0.35%, the band gap of the alloy goes to 0. And after that, the band gap increases again. So this is known as a band inversion. So lead telluride and tin telluride are different by a band inversion at the 4 high symmetry points, L points, in the Brillouin zone. So the band gap is located at these L points, and when you make the alloy, the band gap closes and reopens. So forming, giving rise to this band inversion. So as you have probably heard in the lecture in the first week, this kind of band inversion is usually a sign of some interesting change in topology. But what's special here is that band inversion simultaneously occur at 4 L points. So this is because the 4 L points are related to each other by the cubic symmetry. Okay, the symmetry relate to each other. So with 4 band inversions, the Z2 topological indices stay the same. So neither lead telluride nor tin telluride is a Z2 topological insulator due to time rules of symmetry. They are not. However, this band inversion has interesting consequences when we take into account of this reflection symmetry. Okay, so for that, let me maybe write something here. So if we take a cut in the Brillouin zone, looking at this particular reflection plane, so this plane is at kx equal to 0. So if I look at the Bloch electron wave function as a function of momentum. So reflection will relate this wave function at kx, ky, kz to minus kx, ky, and kz. So at kx equal to 0, the reflection basically relates the wave function to itself at the same momentum. So in this sense, this reflection symmetry in momentum space effectively becomes internal symmetry. It acts as internal symmetry in momentum space. In this particular momentum plane, and so what one can do now is to decompose the single particle block states into two classes. So those, which I call psi plus, has a property that on the reflection, the eigenvalue is plus I. So as I said, the reflection square is minus 1. So the eigenvalues of reflection symmetry is either I or minus I. And there's the second class where the eigenvalues are minus I. So the wave functions on this kx equals 0 plane can be decomposed into these two sectors, those two different mirror sectors. And for each sector, we can define a topological index, basically the Chen number, right, which is an integer. So the sum of the Chen numbers for the two sectors, for the two mirror subspaces, is a total Chen number. And in this case, the total Chen number is 0. It's because the crystal has time reversal symmetry. Okay. However, the Chen number for each mirror sector can be non-zero. And in this case, we define something called the mirror Chen number. And this serves as a topological invariant. So it's an integer topological index. And it's only defined in the presence of reflection symmetry, because only in this case, I can decompose single particle states into two sectors. So one can further show that the band inversion at all these, for example, if I look at a particular reflection symmetry x to minus x, then there's this particular plane that is invariant under this reflection, for which I can define the mirror Chen number. And there are two L points falling onto this plane. And as band inversion occurs, the mirror Chen number changes by 1 at L1 point and by 1 at L2 points. The change of the Chen number at L1 and L2 are identical. So what this means is basically after band inversion, the mirror Chen number, being the integer index, changed by 1 plus 1, which is equal to 2. So this says the two sides of the phase transition have different topological indices, and they differ by mirror Chen number 2. So one of them got to be a topological index. So you see that this is a way that an even number of band inversion can still lead to topological phase. It's because this topological index is an integer. Okay. On the other hand, in contrast, for a time reversal invariant topological inverse, the index is a Z2, a binary quantity. And in that case, if you take into account the fourth band inversion, it adds up to 0 mod 2. That's why it's not a topological phase with time reversal. So later, I will show that it turned out that if we go beyond the framework of non-interacting electrons, the topological indices associated with phases protected by reflection symmetry is not integer, but Z8. It has to do with effective interactions. Okay, but for now, let me just stick with the band theory. Z8. So this is for insulators with charge U1 conservation and spatial reflection symmetry with interactions. It's integer Z. Yeah, it's just here. It's this mirror Chen number. It's Z, but with interactions, it reduces to Z8. And actually, there's a fairly straightforward way of showing that. I'll get to that. Not yet, but at the end of this lecture, I'm hoping to show it. Yeah. Yes?
So at least this definition can rely also on translation.
Yes, but also I will show you that it in fact doesn't. This is actually an excellent point. So whenever we talk about spatial symmetry, the natural question to ask is that how robust it is. For example, if we have disorder would violate translation symmetry and all rotation symmetries, reflection symmetries. But it turns out, again, I'm going to show later in this lecture that reflection symmetry does not destroy this phase. So in fact, the surface state is fully robust even against strong disorder. Yeah. Yeah, exactly. I'm not writing it. So what actually happens? Yeah. So exactly. So M actually is the action of M is actually in terms of the its action on the spin. It's represented by minus I sigma Sx. So this is reflection x to minus x. So you see that if the spin is pointing in the x direction, reflection does not change the spin eigenvalue. But if it's y and z, it will flip the spin. Yeah. So it's, and with this, m squared is minus 1.
There's no complex.
There's no exactly. That's very important. Yeah. Yeah. Actually, absolutely. It's a unitary symmetry. It's a unitary spatial symmetry. Yeah. Yeah, actually, that's an excellent question. For this particular structure, this rock salt structure, ky equal pi is the same as ky equals 0. Kx equal pi is the same as, yeah. This has special to this rock salt structure. Yeah. So L1 and L2 lie on mirror reflection around about the x-axis. Well, actually here. Actually, yeah. So let me define it properly. So they are the reflection symmetry. The reflection plane is along the 1, 1, 0 axis, but they are equivalent reflection planes about 1, minus 1, 0, 0, 1, 1, 0, 1, minus 1, etc. So let me now focus on a particular reflection symmetry. So and for in this case, in this coordinate, I call it. Yeah, I think in this coordinate is part of y to minus 1. Anyway, so for particular reflection symmetry, there are 2 L points that lie on that plane. Yeah.
So the L1 some other
L3 and L4. I mean, L3 and L4 will lie on another reflection plane.
L1 and L2
They are this plane.
1 minus 1.
Yeah. Yes.
Given multiple mirror symmetries, say x, y, and z,
Yes.
multiple mirror symmetries?
Absolutely. Yeah. And in this particular compound, all these reflection symmetries are symmetry related by rotation symmetry. So the mirror number on these planes are all equivalent. But for simplicity, let me just talk about one mirror plane. And imagine that all other symmetries are gone, let's say, with only one reflection symmetry left. So then this band inversion between lead tenoid and tin telluride should lead to one topological phase, either lead or tin telluride. Okay. So okay, so the question is now which one, right? Which one is non-trivial? And this is a general question we ask in finding topological integers within band theory. Basically, the change of topology can be inferred from band inversion, which is described by a massive Dirac fermion with a mass-changing sign. However, to determine the topological index itself, the absolute value of topological index for a given material, that requires material-specific studies. For example, the first principle calculations. So by just knowing that the band inversion, the fact of the band inversion exists, cannot tell us which of the two is topologically non-trivial. So for that, we look at first principle calculations, so for this is the actual band structure in the vicinity of the L point, and you see that conduction valence bands come close to each other, forming a Dirac dispersion, massive Dirac fermion dispersion, and this dispersion for lead telluride is very similar to tin telluride. Okay, but the difference is that the sign of the Dirac mass is opposite in the two cases. Now, to infer the sign of the Dirac mass, we need to look at actually the wave function of the block states in momentum space. Okay, so these K, L, gamma are high symmetry directions in momentum space. So here, the size of the red dots denotes the weight of the wave function on the tellurium orbital. And you see that for lead telluride, the occupied states in the valence bands are dominated by tellurium orbitals. So this is expected because this is expected for an ionic insulator because lead is cation, tellurium is anion, just like sodium chloride. So if you make have such an ionic insulator, the electrons are basically transferred from the cation to the anion. And in this case, when this happens, you know that this material has to be an atomic insulator because it's adiabatically connected to a Slater determinant of localized electrons on tellurium, right? So this is topologically trivial. So on the other hand, if you look at tin telluride, the occupied states are mostly tellurium in momentum space, but just near the top of the valence band, that the wave function in the occupied states come from tin, from cation. So this tells us that tin telluride is intrinsically inverted. The wave function has a mixture of ionicity and covalency. So this, combined with the fact that we know that has to be a topological difference between the two, so that led us to the conclusion that tin telluride must be topologically non-trivial, protected by mirror symmetry. Yes?
Is there a particular philosophy that when you're searching for PCIs, you shifted from general search, broad search?
So in this particular case, we first use this band inversion to infer that there's a change in topological index. So then we have 50-50% chance of getting it right. And then we look at first principle calculations. And from these orbital character of these wave functions, that led us to a conclusion.
With finding materials with generally band inversion.
Yeah, that's always a good strategy. And in this particular case, later we also actually calculated the Miracle number numerically. So it also fits. Yeah. Yes?
Why did you look at these materials instead of sodium chloride?
Yeah. Well, for sodium chloride, we know that cannot be topological in the first place. But the actual way we got into this is quite accidental. So we were actually initially studying properties of superconducting lead telluride, superconducting tin telluride for some other purpose. But then, so it's very accidental actually. So anyway, so yeah, that's yeah. All right. So anyway, so in this particular example, as is shown here, band inversion occurs between the cation and anion, which is actually a very special example, which is a special case. Unusual case, for example, in other topological insulators like bismuth telluride, bismuth antimony, and many others, band inversion is basically occurring between either the s and p orbital of the same atom. For example, in mercury telluride, band inversion occurs between the s and p orbitals of mercury, or it occurs between the covalent bonding and anti-bonding orbitals. And this is a rare example where band inversion is between cation and anions. So I think this is related to some of the interesting chemistry in these materials. All right. So so indeed, one of the features of the topological phase is the presence of surface states. And here we see that indeed, from our calculation, we see that these are bulk states. But then inside the band gap, there are these surface states that cross each other, leading to the presence of drag cones on the surface. And one thing I want to call attention to that in this case, with topological phases protected by mirror symmetry, the surface states are still linear, have linear dispersion. They're still Dirac fermions. However, the important thing is that the Dirac fermions are located away from any of the time-Russell invariant momentum. Okay, this is because the protection here has nothing to do with time-Russell symmetry. In fact, if we break time-Russell symmetry, these Dirac cones are still present. So they are located instead on the reflection invariant planes. For example, this line is invariant on the x go to minus x. So, the Dirac points are forced by reflection symmetry to lie on this plane. So they can move smoothly along this line, but not away from it when mirror symmetry is present. And one way you can see that these Dirac cones has to be present is to take a cut. For example, if I look at this particular line, kx equals 0, and look at the dispersion as a function of ky. Okay, we know that on this line, the Miracle number, there's a Miracle number associated with a two-dimensional band structure on this kx equals 0 plane. And the Miracle number being 2 guarantees that on this line, there has to be 2 modes moving to the right and 2 modes moving to the left. So this is exactly what is causing the crossing here. The 2 bands that cross each other have opposite mirror eigenvalues, plus I and minus I. And that's why the band crossing is robust. So if I plot the energy as a function of ky on the plane kx equals 0, what we will find is that there are bulk states, but inside the band gap, there are two modes moving to the right with mirror eigenvalue plus I, and two modes moving to the left with mirror eigenvalue minus I. So that's why the crossing is protected by mirror symmetry. Moreover, one can deform the band structure in a smooth way, so that, for example, these Dirac cones can move towards each other, and eventually they come to the same location at the gamma. Okay, and because the particular topological index being non-zero, it guarantees that even when these Dirac cones merge on top of each other, they cannot pair annihilate. They cannot. So yes.
I guess I'm wondering, suppose you just have some odd vacant.
Yeah. So disorder always break mirror symmetry locally, but by definition, disorder preserve mirror symmetry on average. So I'll show later that provided that mirror symmetry is on average present, these surface states are robust. I'll give you an argument for that. Yeah.
Really on average.
Yeah, but you see that is required, because if on average mirror symmetry is not present, is absent, then we will say this crystal doesn't have a reflection symmetry.
So you will explain why you just have a realization of the
Yeah, so then I'm sort of relying on this fact that sort of ensemble average. So in other words, one question we can ask is the surface still metallic? Can this be localized? So I'll give an argument that it cannot be localized. Yeah. Okay, yeah. So okay. So this is let me just continue that the despite the presence of 4 Dirac cones, and despite that the position of the Dirac cone can change along these lines, so the Dirac cones can merge onto each other, but still, even in that case, they cannot pair annihilate. So this is different from any two-dimensional material. For example, in graphene, the Dirac cones, in pristine graphene, Dirac cones are located at the corner of the Brillouin zone, but if you stretch graphene in one direction, the Dirac points can move toward each other, and once they come to the same momentum point, they can pair annihilate. So here, these Dirac points can move, but they cannot pair annihilate. It's because of the topological index being non-zero. So this is what we call topological protection. So as long as mirror symmetry is present, they stay gapless. Okay, so yes. Yeah, absolutely. So I have a plot here. So the good news is that there are infinite number of surfaces which preserve this mirror symmetry. So for example, if this is a reflection plane, so right now I looked at the top surface, but I can also rotate this surface orientation, right? As long as the surface is perpendicular to the mirror plane, that surface will have this reflection symmetry. So all the surfaces that are perpendicular to a mirror plane are guaranteed to have gapless surface states. But their property will be very different. So for example, in this 001 surface, there are 4 Dirac cones, but it turned out in other surfaces, some of them only have 2 Dirac cones. Some of them project to each other. Actually, that's an excellent question. This already happens for the top surface, the 001 surface. So this is exactly what I'm going to describe now. Yeah. So if you look at why these Dirac cones come about, you see that on the 001 surface, the 2 L points, L1 and L2, would project on top of each other to the end point. However, the Dirac cones are not located at the end point. They are located away from the end point. They come in pairs. So how did that happen? So this is explaining this. Okay, let me describe this. So one can first take a zeroth order approximation. We say that every band inversion in the bulk generates a massless Dirac fermion on the surface at the location that is the projection of momentum onto the surface. So then we will immediately see that L1 and L2 project to the same momentum. So it leads to 2 Dirac cones on top of each other located right at the endpoint. So that's a zeroth order approximation. And this is in fact what you would predict from a continuum theory based on domain walls. So in other words, if I have a very smooth interface between lead telluride and tin telluride, right? If the alloy composition changes smoothly from lead telluride to tin telluride through the whole series of alloy composition, spatially, right? So then you would indeed have this situation. However, remember that the actual surface is atomically sharp. So then we should consider all kind of allowed perturbations that connect these two Dirac points, hybridize these Dirac points. So this is described by this here. So the starting point is two copies of the Dirac surface states, kx plus y minus ky as x. The two copies is represented by an identity, an extra index. So this extra index tau represents L1, L2, the two values. And because the two values project to the same momentum, we are allowed to write down terms that connect the two values. So the two values basically are separate in the bulk because their momentum kz is different. But on the surface, kz is no longer a good quantum number, so there are inter-value scattering processes. And the inter-value process are off-diagonal in the value index. So it's either tau x or tau y. Now, one can enumerate all possible symmetries and write down all allowed terms. And these are the only two terms that are allowed. So once we add these two terms to this low-energy Hamiltonian, so we find that the band structure changes from two identical copies of Dirac cones to this one. That on the now away from the high symmetry points, there are two low-energy Dirac cones that are generated. Okay, so basically this kind of a inter-valley scattering changes the low-energy properties a lot, but it preserves the high-energy property. So that's why if we look at the actual surface states as a function of energy and kx, ky, it has a lot of features. At low energy, we have the Dirac cones, but at high energy, the surface of the Fermi surface of the Dirac cone are severely distorted, and then above a critical energy, the two Fermi pockets merge with each other. This is a Lifshitz transition, and after that merging, there's one big electron pocket and a small hole pocket concentric around the X point. Okay, so basically, there's a hierarchy of energy scales in this problem, and that is due to this particular fact that the two L points project onto each other. Okay? And again, mirror symmetry plays a crucial role. That if mirror symmetry is absent, there are additional terms that can be added, and those terms will gap the Dirac points, so leading to a gapped surface with no surface states. Okay. So this immediately tells us that when the surface, for example, as a function of energy, when the Fermi surface, the two Fermi pockets merge each other, this is a so-called Lifshitz transition, and that leads to a Van Hoff singularity. The tensile state diverges. Okay. Okay. So experiments came in quickly, and from three groups. The Yoki Ando's group in Japan, they studied both compounds, lead telluride and tin telluride, from photon emission, and you see that lead telluride has a gapped surface state. Tin telluride has this predicted, it has this Dirac surface states, which is away from the X point. Okay, so this one is away from X point. And very interestingly, that in this related compound, lead tin selenide, at high temperature, the band gap is normal with no surface states. But as you lower the temperature, the bulk band structure changes. The bulk band gap decreases and then goes through a band inversion as a function of temperature. So at low temperature with inverted band gaps, you see that again the Dirac surface states appear, again away from the X point. Right. So from the He-Hassan's group, you look at photon emission, and in the entire Brillouin zone, the 001 surface has these four Dirac cones. Yes. Okay. So let me quickly go through some other interesting experiment before I come back to the theory. From STM study on lead tin selenide, if you look at the tensile states as a function of energy, at low energy there's a Dirac cone, but then there are these shoulders. So these shoulders, low peaks in tensile states, are exactly coming from the Van Hoff singularity when the Fermi surface of the two pockets merge onto each other. And now to compare the differences between topological inserters and topological crystalline inserters. In the case of topological inserters, the Dirac cone, there's odd number of Dirac cone, and they're guaranteed to lie on the time-erosion invariant momentum. And in this case, basically, if we think about all possible perturbations that are time reversal invariant, basically, you can only change the energy of the Dirac cone. This is like a scalar potential. But for topological crystalline insulators, because the Dirac points are located away from the high symmetry points, from the time reversal invariant points, so the time reversal invariant perturbations can couple both to the Dirac mass, to the gauge field, and also to the scalar potential. So there's a lot of new interesting possibilities. Yes? Oh, you mean this?
Yeah.
Oh, that's just different. Sorry, yeah, that's a good question. Let me clarify. So this theory, right, is a theory that that describes both low energy and high energy, right? So this theory sort of contains information about the entire energy range. Okay, and yeah. So this is basically a four-band theory. And here, when I come to here, I'm just talking about low energy physics at each Dirac node. At each Dirac node, there are three types of perturbations: scalar potential, Dirac mass, and gauge field. They can all be generated in a time reversal invariant setting. So that's what I'm going to come to talk about now. Yeah. Yes.
So if we consider a TI surface, there's a single Dirac cone, which is anomalous because it cannot be realized in a two-dimensional system. But if I look at the surface,
yeah, I'll come to that. Yeah, it's also anomalous. Yeah, exactly. Yeah. Yes. Right. It has to be restricted in the sense that, yeah, that's an excellent question. So later I'll have a slide, but basically, gauge field. So you're right that if you preserve the mirror symmetry, then gauge field can only have one component, right? But it turned out that if you can also have, even if you break gauge reflection symmetry by strain, okay, it turned out there's another symmetry which locally protects these Dirac points. So that will give you basic gauge field in both with both components. Now, one important thing is that this gauge field is different from the gauge field. The effective gauge field due to strain is different from the gauge field due to electromagnetic field, in the sense that for electromagnetic gauge field, the gauge field at these two k and minus k, they have to be the same. But for the strain-induced effective gauge field, they always come with opposite sign. This is because the strain doesn't break time reversal symmetry, but real magnetic field does. So yeah. So
but it's just gauge field.
Yes. This is UIJ. Yeah, exactly. Just both shear and the what's it called? Both shear and stretch. Yeah, they all act as gauge field. It turned out. Yeah. So this is sort of also a difference between this and graphene. In graphene, you need real shear to act as a gauge field, but in this case, both shear and stretch act as gauge field. Say again? Well, I mean, stretch is a volume preserving stretch. It's like a.
Oh, okay, so that's true.
Yeah. That. Okay, since you're asking, let me maybe just move on. I probably won't have time to talk about it. But yeah, this is what I mean. Does this help? Shear, stretch, and compression. All these contribute gauge field. Yeah. For example, if I have a compression which preserves the rotation symmetry, all Dirac points shift identically towards the center, right? Because the rotation symmetry is preserved. But uniaxial stretch, makes x and y direction different. So on the x direction, they shift towards the center. On the y direction, they move towards the edge. And this is shear. In shear, basically you rotate the whole axis.
But I would have thought the first one was related to scalar.
So this one, I think you're absolutely right that this one could also generate a scalar potential, but it also has a gauge field component. That is absolutely certain. So there's also, for example, there's even first principle calculations for this case. When you have uniform compression, Dirac point shifts by a substantial amount. And actually, I won't show the data, but this kind of a Dirac point shift due to strain has been experimentally observed by VDM at Haven's group in the recent STM experiment. Okay, so I'm going to focus on just one particular distortion, which is a structural distortion that breaks the reflection symmetry. And since I've been emphasizing that the Dirac points are protected by reflection symmetry, so if the symmetry is broken, we expect Dirac fermion to open a gap to generate Dirac mass. So actually, this kind of a distortion, we were actually worried about this in the beginning because we know that, for example, tin telluride in the bulk has a structural distortion at low temperature. And so what would be the effect of distortion on the surface? So the distortion occurs in the following way. So the red and blue are the two atoms, tin and tellurium. So they can move relative to each other along a particular direction. For example, the red dots should be in equilibrium. At high temperature, they're sitting at the center of this square of the blue atoms. But at low temperature, they can spontaneously move away from the center along a particular direction. So this gives rise to this so-called ferroelectric structural distortion in tin telluride at low temperature. Now, depending on the direction of this distortion, we can break either one of the mirror symmetries, x to minus x, preserving the other, for example, y to minus y. Or if the distortion is along some arbitrary direction, then both reflection symmetry will be broken. So this is a phase diagram that all of, for the Dirac fermions located on the surface Brillouin zone in momentum space, how the Dirac mass depends on the direction of the distortion. So the direction of the distortion is represented by a vector, right? It's like a ferroelectric polarization vector. So for example, if the distortion along the 1, 0, 0 direction, along this direction, all 4 Dirac fermions are gapped. But the Dirac mass, 2 of them has a plus sign, 2 of them have minus sign. And if you rotate the distortion along other directions, the sign of the Dirac mass changes. And along a particular 1, 1, 0 direction, 2 of the Dirac fermions remain massless, the other 2 become gapped. It's because along this particular direction, the distortion still preserves one mirror symmetry. So basically, the important thing is that the sign of the Dirac mass depends on the direction of the polarization. So this leads to a very important consequence. So now imagine that I have a domain wall. On the 2 sides, the distortion points along different directions. Okay, and then you see that of the 4 Dirac fermions, 2 of the Dirac fermions have the same sign across the domain wall. The Dirac mass have the same sign, but for the other 2 Dirac fermions, their mass change sign across the domain wall. So whenever we have a 2-dimensional Dirac fermion with a mass change sign, we know that, and these 2 Dirac fermions come in time-reversed pairs. We know that we change the Z2, 2-dimensional Z2 topology index, so that at the domain wall, it has to be helical Dirac fermions, 1-dimensional Dirac fermions. We spin up moving in one direction, spin down moving in the opposite direction, right? So what this means basically is that if we break the mirror symmetry, the surface states are gapped, but depending on the orientation of the ferroelectric polarization, different domains have different 2-dimensional topological index. Okay, so even gapped surfaces are interesting. Okay. And this actually relates to the fact about disorder. So in the presence of disorder, we know that we can imagine that locally the distortion breaks reflection symmetry, so that we have a gapped surfaces. The Dirac fermions all have mass, but because disorder only breaks mirror symmetry in the average way, so there has to be different domains where the distortion points along different directions. So then there are these conducting metallic edge domain wall states, helical edge states. These helical edge states are perfectly protected from localization. So these helical edge states will now percolate throughout the entire surface and make the surface metallic. Yes?
I mean, this is a very similar argument to one that you made earlier for time reversal, but in that case, there was only one Dirac fermion. Now there are multiple.
It's different. It's very different. Actually, for the case of this is actually. Let me first finish this and I'll comment on that. Yeah. So what I just argued is from the point of view of the microscopics that if I have disorder, we have basically an array of domain walls, and the domain we have an array of domains, right, with equal probability. The distortion has to point equally in the 2 directions, and then because the domain wall is guaranteed to be fully delocalized. So we have a percolating path of these domain walls that make the entire surface metallic. And now let me give you another argument, which I think is even stronger. So how do we prove that if disorder breaks reflection symmetry in an average way, how to prove that this region cannot be localized? Okay, so let me imagine a following setup: that if I have a large area where we have a disorder on average break reflection symmetry, but that locally break mirror symmetry, but on average it's 0. And let me sandwich this region between two other regions where I externally break reflection symmetry, okay, by enforcing the distortion in the two different directions. So then I know that if I shrink this entire region to a sharp interface, right, then this interface between these two gap domains has to have one helical edge states. Okay, so now I'm going to argue that based on this fact that this enlarged disordered surface cannot be localized. Okay, so the way to do this is to argue by proof by contradiction. Suppose this disordered region is actually localized. Okay, then we know that this entire region must be topologically equivalent to having one helical modes. And if by assuming that this region is gapped, is localized, then this conducting helical edge states has to be either localized on the left interface or on the right interface. Okay, but we know that reflection symmetry, even on average, would forbid having a conducting path on the left but not on the right, and vice versa. Okay, so this tells us, and furthermore, we know that there's no way of splitting a helical edge state into two components while time rule symmetry is present. So this tells us that with time rule symmetry, okay, so now I'm using time rule symmetry. So with time rule symmetry, the non-magnetic disorder, no matter how strong it is, cannot localize the surface states, provided that mirror symmetry is on average present. Okay.
So
Yes?
Maybe I'm just not getting the point. Why can't those two, they have counterpropagating?
Yeah. Why cannot be? Yeah. No, it's because time rule symmetry forbids backscattering, because the two have opposite spin polarizations. It's exactly like the edge states of a quantum spin Hall insulator. Different.
So if you have like the states in the domain.
Yeah.
So what about
So if I have a one path, right?
Yeah.
No, this path can be a straight line or can be rugged, and then it's guaranteed that it's, time rule symmetry guarantee that there's no backscattering, even if the edge is not, even if it's rugged. Yeah. So it's a property. Yeah.
Maybe mirror symmetry and average and exact and reversal.
Exactly.
Is mirror symmetry and average and reversal?
No, I don't think so. No. Yeah. That's a good question. I don't think so, but I have some argument, but now it will take a while for me to reconstruct it. But yeah. Yeah. If you look at this argument, right? So then, we agree that this entire region, which it could be for a particular disorder realization, and as long as it's substantially large, huh? So we know that if this region is localized, then there has to be a conducting path either on the left or on the right, and that violates mirror symmetry in a macroscopic way. That's not possible. Yeah.
What happens if you just put vacuum
What do you mean put back? You mean cut the crystal?
instead of the disordered surface? Using this argument to show that there has to be conducting path in the disordered surface.
Yeah.
What
It has
about
to be non-localized.
if I just replace by vacuum, which part of the argument break?
But which part you replace by vacuum?
The disordered surface part. Put back.
Oh, then what happens is that the then there's side surface, right? So the top surface has to connect to the side surface, right? Yeah. So yeah, let me also comment that. So basically, there's a difference between sort of being if I compare the topological insulator surface and topological crystalline insulator surface, in both cases, the surface states are metallic, but for different reasons. In the topological insulator with all number of Dirac, this is going back to Rahul's question. For topological insulator case, the surface states are metallic because they have an anomaly. And in this case, the surface states is metallic because because gapped surfaces, if I break the mirror symmetry, gapped surfaces are topologically different. So in other words, the surface when mirror symmetry is on average present is like self-tuned to the topological phase transition of a 2D normal insulator and a 2D quantum spin Hall insulator. Okay, so it's basically delocalization by being critical.
It's not the same argument you and Charlie make for topological insulator with statistical time.
It's exactly the same for statistical time rotation. Exactly. In that case, the system is self-tuned to a critical point between different Chen states. Yeah. So in one case, in the case of a strict 2D topological insulator with time rotation symmetry, a strict 3D topological insulator with time rotation symmetry, the surface is metallic because of the anomaly. And here, it's metallic because of the self-tuned critical point. Exactly. Yeah.
This ferroelectric polarization is quantized.
It's approximately quantized. Yeah. We can discuss later. Yeah. But not exactly. Yeah. I mean, for example, in 2D, the ferroelectric polarization doesn't have quantized units, right? So yeah. Anyway, so all right. So we worry about this distortion, but the good news is that it's known that, for example, in tin terabyte, in the ferroelectric distortion in the bulk actually points along a particular mirror axis, so that even for gapped surfaces, there's one mirror symmetry that remains. Now experimentally, the VDS group actually used STM to look at this compound lead tin selenide. It turned out to be very interesting. So this is an alloy, lead and tin. They mix with each other. So in topography, it's looks like a mess. But when you turn on the magnetic field, you see that the beautiful lambda levels show up. These are lambda levels coming from the surface states, and actually the mobility of the surface states is extremely high, so that you see the lambda level energy is basically independent of position over a length of 30 nanometers or even longer. So the quality of the sample is pretty good. So there's a lot of features in understanding the how the lambda levels depends on the magnetic field. I won't go into the details. For example, you see that the lambda level index jump at a particular energy, which corresponds to the Van Hove singularity you see at zero magnetic field. And this is precisely because that above and below that critical energy, we have a change in the topology of the Fermi surface, with two disconnected Dirac pockets in a low energy. It evolves into a big pocket at high energy. So that's why at this transition critical energy, the size of the Fermi surface for cyclone orbits doubles. So that's why the lambda level index changed from 3 to 6. There's discontinuity here. So I want to go into the details, but one thing I want to point out is that a particular feature is that there is one lambda level whose energy is independent of the magnetic field right at the Dirac point. That's what we expect, from graphing the special zero energy lambda level. But there are two additional lambda levels on both sides of the Dirac points whose energy are also independent of magnetic field. So this was initially a puzzle, and then we realized this is exactly what we expect for a massive Dirac fermion due to structural distortion. Okay, so if we have structural distortion, Dirac fermion open up a gap, but the Dirac mass at k and minus k has to be opposite. So when Dirac fermions have a mass, the zero energy lambda level is shifted either to the valence band top or the conduction band bottom, depending on sign of Dirac mass, but this is still independent of the magnetic field. Okay, so this explains the three peaks that are independent of field. So based on this experimental data, we infer that a distortion occurs along a particular mirror axis, 110, so that one mirror symmetry remains present along this mirror symmetry is present, two Dirac fermions remain massless, and the other two Dirac fermions are gapped with mass of opposite sign that is guaranteed. So these two Dirac fermions give rise to two degenerate zero energy lambda levels in the middle, and these two massive Dirac fermions with opposite mass give rise to lambda levels on the sides. Yes?
Trivial question. In the previous slide, you said this is on lead and selenide.
Yes. It's what?
Is it then lead and
selenide? Lead tin selenide. Yes, also TCI, yeah. So in all these cases, the high tin concentration are topological, and the high lead concentration are non-topological. So and with a former student Maxim, we are able to fit the lambda level over a wide energy range by just using 2 parameters. And actually, from this experiment, the Dirac mass we inferred is 11 millielectron volt. Basically, it's the energy spacing between the lambda levels of the non-dispersive lambda levels. And more recently, the VDS group continued to improve the imaging topography, and now they can really see the distortion from topography. So again, this is the looks like a mess because it's an alloy, lead, and tin mixed with each other. But if you average over the position of atoms over large areas, you can reconstruct an average unit cell, and you see that from this figure that I think you see this zigzag-like feature, so that this reflection symmetry is still present, but the other reflection symmetry is now lost. So this tells us that structural distortion is really present. And further, there's a bulk X-ray scattering experiment showing that in Latin cylinder at this alloy composition, the bulk is actually still non-distorted. So the distortion only occurs on the surface. There's also recent photoemission experiments from the Poland and Sweden group, and also in photoemission, you see that at low temperature, the distortion onsets. Okay, it's at around 100, 200 Kelvin. I've got, and above that temperature, the Dirac fermion is massless, and below the temperature, the surface Dirac fermion acquires a mass. Okay, so how much time do I have? 20 minutes? Oh, 20, okay, all right. Still, okay, all right. So, speaking of applications, proposed applications. So with this topological crystalline, we now understand it in a bulk form, and let's now consider what happens in the thin film geometry. We have a thin film. Now, one thing I want to emphasize is that, so this is this is about 20 nanometer thick band structure calculation. That you see that in the bulk crystal, the surface state has these Dirac points that are located away from the gamma point. They form a Dirac point. But when you take into account of the top-bottom surface hybridization, there's a small gap opening. And if you further reduce the thickness, okay, this hybridization gap further increases. So the band structure changes a lot as you go from thick to thin limit. But one thing I want to emphasize is that even in very thin samples, all these bands that you see in the two-dimensional system are actually the remnants of the surface states in the 3D limit. Okay, so in other words, if I compare band structure of thin films of tin telluride and lead telluride, they are very different, because in lead telluride, in the 3D limit, there are no surface states, but in tin telluride, there are. So even when you take a thin film, when the top and the bottom surface states strongly hybridize to open up a gap, the low energy band structure are basically coming from the hybridized surface states. They are very different from the bulk states. So recently, together with the Tsinghua group, we studied these thin films. So these are atomically thin tin telluride that's grown on graphene, and here's what experimenters found an interesting surprise. That's not what we theoretically expected. So as I said, tin telluride has structural distortion in the bulk. Unlike lead tin selenide, the distortion occurs at around 90 Kelvin. It's a fairly low temperature phenomenon. But when the tin telluride is atomically thin, in the topography, you see that there are different stripes here. So these stripes are different ferroelectric domains. Okay, and you know that because if you look at the DIDV spectrum as a function position, whenever you come to each of the domain wall, you see that the bands either bend up or bend down. Okay, this is telling that there's a build-up of the charge. There's a net internal electric field that is caused by band bending. And if for a given domain, if you move to the left and to the right edges, the band bending goes in opposite directions. Okay, so this is evidence for the structural distortion that generating a ferroelectric polarization. And also this is confirmed by the quasi-particle interference, which shows that the lattice Bragg peaks actually splits and distorts. Now, looking at this distortion as a function of temperature, we found that the distortion actually goes to very, very high temperature. In one unit cell, 2 atomic layer thin terawatt, the distortion is around onsets around room temperature, slightly below room temperature. But for 2 or 3 quintupole layer thick samples, the distortion, is present even at room temperature. Presumably even at much higher temperature is still present. So, so this is a rare example. Okay, that there's a robust in-plane ferroelectricity in atomic thin materials, and usually that if you take a bulk material and make it very, very thin, the ferroelectric transition temperature goes down. But here it goes up. So we don't completely understand why, but we think that it may have to do with this particular band structure that come from the hybridized surface states. Yeah. Yes, but yeah. Yeah, but what happened? Yeah, that's actually it's very important. I think in this experiment, graphene is chosen as a substrate. It's because in graphene, this van der Waals bonding, so the substrate does not actually cause any stress or strain to the sample. So it's basically essentially a stress-free environment. So that's actually important. Yeah. So yeah, so this is as I said, this is we don't completely understand why the ferroelectricity is so enhanced, but my own speculation that it has to do with a particular band structure arising from hybridized surface states, and we are still looking into that. So this with this effect, my postdoc Jingwei Liu sort of played a leading role in proposing some device that if we this ferroelectric polarization, you can think of it as like in 2 different directions. You can think of like a classical bit, 0 and 1, and because it causes bending at the edge, if you look at the tunneling current from a metal into this atomic thin material, the tunneling current will depend strongly on whether the bending goes up or goes down. In other words, it's a way the tunneling current depends on the direction of the ferroelectric polarization. So it can be used to read out these bits. And actually, the Tsinghua group followed this proposal. They did this experiment, and in fact, you find that the on-off ratio, right, as you switch the ferroelectric polarization by a voltage pulse, the tunneling current is different by about 3,000 times. So the on-off ratio is 3,000, and this is done at room temperature. Okay, so this perhaps could be used as some sort of a ferroelectric tunneling random access memory. In conventional memory, every time you read it, you destroy the state. You have to write immediately. But in this case, the ferroelectric polarization is really stable at room temperature. So you do this readout without having to write again. So you don't destroy the bit. Yes?
Does the polarization have anything to do with the chemical edge state?
So one thing we are currently thinking is that if you look at this domain wall, right, in the thick limit, if I have this distortion, then you exactly would have a helical edge states. So now in such a thin film, probably the top and bottom surface have already hybridized, but you still expect that, for example, this region may be metallic, that everywhere else has a big gap of order 1 electron volt. Okay, the band gap actually has increased dramatically when you go from the bulk to such a thin film. But we expect that the gap here should be much smaller, because it's coming from the helical edge states that are hybridized. Yeah, so and actually, one thing you notice that if you look at the ferroelectric distortion for this geometry, right, they are off by 90 degrees, and the perpendicular component of the ferroelectric is actually the same. So you don't expect any charge accumulation based on just electrostatics, but we think there should be helical edge states due to this topology. Yeah, so we're still looking at that. Yeah. All right. So okay. So in the next last 10 minutes, let me switch a bit to interacting states, interacting systems. So as I said, this Mirror-Chen number is entirely based on theory of non-interacting electrons within band theory. We talk about single particle states in momentum space, and everything is very sort of tied to the details of band theory. But now we can ask a general question: is there a classification for interacting systems, interacting insulating states with charge U1 conservation and a spatial reflection symmetry? And the answer is that that interaction actually dramatically changes the classification. It changes from integer topological index to Z8 in 3 dimensions. And I won't go into the full detail of how this reduction occurs, but let me at least give you the flavor, the general idea. And actually, somebody was telling me yesterday that there's no lecturer has explained so this kind of phenomenon, interaction enabled reduction. The first work, the pioneering work, was by Alexei Kitaev in the case of the one-dimensional topological supernetters in this BD1 class. There, the topological index is again integer within the sort of the band theory framework, but with interaction, it reduces from integer to Z8. Z8, yes. So in other words, when you have there's 8 Majorana zero modes under the end of a one-dimensional topological superconductor, they can open up a gap. Okay, so let me very briefly sketch sort of the idea behind that reduction, and which also connects to here. So if I have a 1D topological superconductor in class BD1, if the topological index is 1 in the bulk, there's 1 Majorana modes. In general, if the topological index is n, there will be n Majorana modes. Okay. Now, symmetry guarantees that any bilinear term is forbidden because in this particular symmetry class, the time reversal acts as complex conjugation. So bilinear operator comes with imaginary prefactor I. It's odd under time reversal for this case. However, quartic interactions, J1, J2, J3, J4 are allowed. Okay, so the question is now, with these quartic interactions, can we gap the edge modes without breaking the symmetry? So it turned out that you need n equal 8 leads to a gapped, fully gapped spectrum with no degeneracy. And one way of understanding that is to think of 8 Majorana fermions as 4 complex fermion states. So then one can consider a familiar problem that if I have 2 orbitals and each orbital comes with a spin, so that in total makes 4 complex fermion states corresponding to equivalent to 8 Majorana fermions, right? So if I have 2 orbitals, let's say A and B, with electrons spin up and spin down, we can write an interaction which is like this, some antiferromagnetic spin exchange interaction. So when you rewrite the spin operator in terms of either the complex fermion or the Majorana fermions, let me schematically write like this. So this bilinear spin interaction corresponds to a quartic fermion interaction, right? So that it preserves the desired symmetry. And we know that with antiferromagnetic spin exchange interaction, we have a unique ground state. It's a spin singlet. So this explicitly shows basically that the interactions, quartic interactions, preserving the symmetry can actually fully gap the boundary modes. Yes?
Can you elaborate a little bit in terms of describe your
So
don't completely gap it out. Different.
Oh yeah,
Before,
yeah. You mean what happens in that
What are
case?
the different patterns?
What are different patterns?
Well, so you can add 4 gammas.
Yes. Yeah. So if you have 4 Majoranas, right? For example, if I have 4 Majoranas, that I can describe. So there's one single term you can write down, which is the product of all these 4. So for that, it partially lifts the degeneracy, right? Because the product of 4 Majoranas is fixed to be 1, let's say, by interaction. But there remains a twofold degeneracy. Because if I have a 4 Majorana fermions, right, the total degeneracy is fourfold. But with this single interaction term, it removes twofold degeneracy, but it leaves another twofold. Yeah. So is it clear?
But then when you get to 8,
You get to 8, you can write down this interaction, which fully removes the
and
degeneracy.
The 8 is how many values J1, J2, J3?
So I can just use this interaction, which is a bilinear spin interaction, but I can rewrite the spin operator in terms of Majorana's. And
I'm
this,
just asking, what is the 8 when you in terms of, is that the number of values of the index can take on?
yes, each index, J, exactly, yeah, sorry for yeah, each index can take value from 1 to 8, yeah, exactly, yeah. So and that's why it maps to this model, right? Because I have 2 orbitals and 2 spins, so in total
Like,
4.
If it's less than 8, then you can't.
I cannot do this, exactly, yeah, sorry. Yeah. Yeah. I'll come to that. Yeah, I'll come to that. Yeah. This is different. So I'm going one dimension higher first, and then 2 dimension higher. So okay. So let me now first talk about a 2D topological crystallizer. In this case, I'm talking about up-down reflection symmetry. But as you can see, that in this case, it's really a bit cheating, because in this case, up-down reflection symmetry acts just as an internal symmetry, as a 2D system is concerned. But later we will go to 3D. Okay, let me do a warm-up first. So yeah, these are the 2 symmetries. I have a U1 charge conservation symmetry and the up-down reflection symmetry, which acts as an internal symmetry. And then again, if I take the non-interacting system, I can define the mirror Chen number. I can decompose single particle states into 2 sectors, and each sector has a Chen number. That's an integer index. So in this case, if the index is n, I will have n right-moving modes on the edge and n left-moving modes on the edge, right, with opposite mirror eigenvalues. And any bilinear operator is forbidden. Any backscattering operator, psi L, psi R, is forbidden because it's odd on the reflection. But the question is on, can we use interactions to gap those edge states? So again, I'm not going to the details, but the answer is that when there are 4, these are not complex fermions instead of Majorana's. If I have 4 right-moving complex fermions, 4 left-moving counter-propagating fermions, we can gap it by interaction. And let me, instead of going into detail, let me just give you an analogy. So if you look at how the mirror symmetry acts on the right and left moving modes, right, it pick up a factor I or minus I. So this is exactly the same as if I have a strict 1D system, but with translation symmetry, right? So then if I have half filling, the Fermi momentum is located at momentum pi over 2 and minus pi over 2. So the translation symmetry exactly has eigenvalue I and minus I. So effectively, we can think about a 1D system with translation symmetry and ask, can we gap it out without spontaneous breaking translation? Now, if you have 4 modes, which corresponds to 2 one-dimensional wires, each of them is spinful, then we can have a run singlet phase, right? So you have run singlet phase, which is, so these are the 2 wires, right? 1 and 2, and I can even build a tight binding model at half filling. We have, each at momentum pi over 2, minus pi over 2, we have left and right moving modes. Backscattering is forbidden if I have translation symmetry. And when I have, 2 wires and each being spinful, I have 4 and left and 4 right movers. And we know that if I turn on the Hubbard U on each wire and I turn on the antiferromagnetic spin interaction between the 2 legs, we can go into a gapped phase where each run here form a spin singlet. So that's a fully gapped state, and it preserves translation symmetry. It does not enlarge the unit cell. So then the same kind of interaction can be written down in the Bostonization form for this problem. You just replaced translation by reflection symmetry. So this tells us immediately that for 4 left and right moving modes, we can gap it out by still preserving the symmetry. Yes?
I didn't really, before I understand the interactive case, I didn't really understand the case, right?
Oh, yeah.
So you have I and minus I.
Yeah. Each has a Chen number.
Right. So why is it?
So I'm assuming the total Chen number is 0. Right? Because if the total Chen number is non-zero, that's like an independent topological index. So assuming the total Chen number is 0, then the only independent index is just the Chen number of the plus I sector.
Why is it?
Because Chen number is an integer. Yeah, Chen number is integer. Yeah. yeah, if you think of this mirror as like a spin, mirror plus I minus I as a spin, then this mirror number is like the spin Hall conductance. Right? Yeah, so you can think of that way. Yeah.
I also think of the C4 classification as starting from the C2 classification of 2dpi and sort of somehow the reflection symmetry enlarges from
You can also think that way. Yeah, exactly. You can also, in other words, one way to construct these is to take a 2D TI like the K-Mallee model, which also has mirror symmetry, and then make n copies of it. Now, if mirror symmetry is present, then even when this index is an even integer, it's still, you cannot add any term that backscatter the edge states. Yeah, you can always construct that way. Yeah. All right. So so this tells us if I have a two-dimensional TCI protected by this up-down symmetry, the classification with interactions is actually Z4. But I said, 2D is a bit cheating because 2D, the mirror symmetry is really the internal symmetry. Let's now move on to 3D. Okay, anyway, this is early approach. Let me actually describe how to explicitly gap out. So what I'll show is that when n is 8, then we can explicitly gap out the edge states. So what I can do is the following. Let me construct a series of domains where, let's say, I have a ferroelectric distortion like this. So the polarization points in opposite directions. No, suppose I only have one mirror symmetry, which is x2 minus x, right? So I have a periodic array of such domains where the polarization points in opposite directions. So now if I look at reflection about x equals 0, about this plane. So this setup still preserves reflection symmetry. So within each domain, reflection symmetry is broken, but because the domains are arranged in an alternating fashion, the overall surface preserves reflection symmetry. Okay. So then we know that, let me start with the non-interacting limit. Each domain are fully gapped, but the domain wall have gapless edge modes. So one can arrange it in such a way that in each domain wall, I have n over 2 left movers and n over 2 right movers. So I'm not going through details, but you will find out that if n is an index for 3D TCI, each domain wall will have n over 2 left mover and right movers. Okay, but then, as we just said, that when n over 2 is equal to 4, each domain wall can be gapped by interactions. Because in this case, the reflection symmetry acting on the domain wall is exactly the internal symmetry, just like the edge of a 2D TCI, right? So this immediately tells us when n over 2 is 4. In other words, when n equal to 8, this whole surface can be gapped out by interactions. Okay. So so I think that's pretty much it. That we show that just describe that with interactions, the non-interacting classification for 3D topological phase reduces from integer to Z8, and more recently, with Mike Hermele's group, I think Mike's probably not here. Yeah. All right. Anyway, all right. Anyway, so with Mike Hermele's group, we actually took one step further. That in addition to these reduction effects, there are also new types of interaction-enabled phases that does not have a free fermion limit with reflection symmetry. So basically, we take stacks of these two-dimensional stacks of the so-called E8 states, the bosonic integer quantum Hall states. And again, if we arrange it in an alternating fashion, in the absence of mirror symmetry, the topological classification is trivial because we can just dimerize different planes. Let me just maybe briefly sketch it here. So we take, so the general idea is that, so this is one thing to emphasize, that's also be used in the next lecture, is that, I've described these topological crystalline inserts, in a very complicated way, starting from momentum space and then think about interactions. But actually, as far as, theoretically considerations, right, goes, the topological crystalline insert with mirror symmetry can be understood as just by stacks of 2D systems. In each 2D system, mirror symmetry acts as an internal symmetry, so there's a mirror to number. And in particular, if I arrange an array of just integer quantum Hall states, let's say, right, with chiral edge states, then in this three-dimensional array, if there's no end, not if spatial symmetry is absent, we can just dimerize these planes so that we can get a fully gapped surface with no surface states left. But if there's a reflection symmetry, okay, let's say with respect to this plane, it cannot dimerize to the left or right. It has to be done, coupled equally to the left and to right, and then you can find that the surface states actually get back to direct fermions in the continuum.
Does this argument depend on whether you have odd or even number of poles?
No, this works in the thermodynamic limit. If I imagine I have, yeah.
You add another layer that you can just dimerize, so the center is really good. Center is in between the layers.
No. The center is actually on the layer. It's very important. For this construction, the center is on the layer.
Yeah, that means you need odd number of layers.
No, but if you have periodic system, right, then there's another layer at infinity. Yeah. So basically, yeah, as far as theorists are concerned, TCR with mirror symmetry are just equal to stacks of 2D topological states. And we will see that this also is true for the other topological crystals that we know of. So now from this, we immediately are able to get a generalization for the interacting enabled phases, because it's known that in 2D, in addition to integer quantum Hall states, there's another kind of a symmetry protected states. There's another kind of a non-fractionalized states, the so-called the bosonic integer quantum Hall states, the E8 states. So if you take an alternating stack of E8 and so E8 conjugate states, then mirror symmetry forbids us to gap the top surface. Okay. All right. I think that's it for today's lecture. There's some strain-induced gauge field, but I'll skip that. So yes, let me just stop here. Thank you. Questions? Okay. No, that's good. No, that's a question yet. Yeah. So once we could put disorder in the bulk as well, but so the argument goes as follows: we first think about whether the surface states can be localized in the presence of disorder. Then what I've argued is that even at sufficient strong disorder on the bulk, the surface remains metallic, right? So this tells us that this presence of these delocalized surface states, even in the presence of strong surface disorder. So this implies that the bulk is a topological phase. Now, if I have disorder in the bulk with weak disorder, the topological phase cannot immediately go away, because topological states is robust, by the presence of the energy gap. So even if I have small disorder in the bulk, it's still robust. But if I have sufficiently strong disorder in the bulk, then the bulk can go through a topological phase transition to become a trivial Anderson insulator. But that's the same for all topological classes. So in order to infer whether the topological phase is stable against disorder, it's sufficient to just ask first whether disorder destroys the surface states, whether surface disorder destroys surface states. So the defining property is that the topological states has to be robust against arbitrarily strong disorder on the surface. So that's the criterion, at least for the fully robust topological states. Now, one thing, speaking of disorder, I think there's a lot of so in the next lecture I may say a little bit more, but there are many, and now by now there are many topological states that rely on spatial symmetry. So I've focused on insulating states. But if you think about all the topological semimetals, wild semimetal, direct semimetal, spatial symmetry is certainly playing a role. The wild points, for example, is relies on translation symmetry. Wild points with different chirality live on different parts of the Brillouin zone, right? They're separated in momentum space. So many questions can be asked, like the effect of disorder and etc. How stable these topological phases are with respect to disorder. I think some of them are, some of them maybe not. Yeah. So. Yeah. Yes.
So here in this picture, you're in the
2D things. Yeah. Yes, exactly. Yeah.
But it seems like I don't know, reflection about
No, in the next plane, it's also reflection, right? All these planes are reflection centers, right? But in between the planes, not.
right, but like reflection about x equals 0 won't act on such way on the
So I'm thinking about a periodic stack of so in other words, there's really infinite mirror planes. Yeah. I mean, I guess theoretically you can also. I mean, with this example, right? This particular mirror symmetry, even if we let's say break translation symmetry, then this is still robust because this particular mode on this plane cannot go away, right? So yeah, even if you break translation symmetry with this particular construction, is still robust. Yes, question. Yeah, that is the case both from non-distortion in the bulk of that 10 terabyte. It's also the case from the recent experiment by VIDIA on lead-tin selenide, where distortion only occurs on the surface. And even for this experiment, ultra-thin few layers of 10 terabyte, the distortion is also along this particular high symmetry axis. Yeah, it just seems to be the case. In principle, it could point in other directions. Yeah. No, then the surface will be fully gapped, right? Yeah. So, yeah. So what happens is that if you take, for example, n equal 1, then you cannot. For n equal 1, then you have just a single direct cone, right? Like very similar to TI actually in that case. Then you can make an alternating domain wall. But in domain wall, you only have chiral fermions instead of helical fermions. So the minimum if you have n equal 2, you have 2 direct cones, as I showed for 10 terabyte, right? If I have a direct points at k minus k, right? That corresponds to mirror number 2. Then if I make the domain wall, there's helical fermion with one left mover and one right mover. So that's why there's a factor of 2. Yeah. Okay. Yeah. Thank you. Yeah. Yeah. Hi.
Can I ask another question?
Yeah, sure.
So if we don't have that the surface protects any symmetry, so let's say the bulk has this mirror symmetry, but
Yeah.
the surface
Does not. Yeah. Then.
Yeah, what can you say about robustness?
Yeah. Well, then the question would be then, what are the measurable signatures? One question is that. I actually don't know.
Okay.
And I know that Ashwin has studied some of these type of systems, and they are looking at like entanglement spectrum. So entanglement spectrum you can make an entanglement cut in a way that still preserves the symmetry, even though the surface does not.
Okay.
And then they have some study of that. But I certainly think that if the bulk has some symmetry but the surface does not, then the surface